Today we're going to do a little bit of linear modeling, and what linear modeling means is we're going to take some quasi real world situation, or maybe an actual real world situation, and we're going to try to model it and mathematically set it up with equations, tables, and graphs so we can study the situation mathematically. And this is what a lot of mathematics is built for, is to actually model real life scenarios using the math that we have. Now, actually, this chapter started with linear modeling, but it wasn't called that at that time. It was just trying to motivate the whole chapter. It started off with a bicycle example where Juan was building some bicycles and he got paid a certain amount plus a certain amount for each bicycle. So we're going to come now full circle with all these new words and tables and equations we have available and just see how that can all work in a real world situation. And a simple real world situation here, and the homework asks you to do, slightly more complicated, but basically the thinking will be the same. So here's today's example. Christine runs a window washing service. She charges a flat fee of $5 plus $3 per window. This flat fee that often is charged by people sometimes surprises people, and they don't like it very much when they first learn about it in math. And the reason that flat fee is there is, Christine's going to get paid $5 whether she does any windows or not. And we're paying her to come to the house and her gasoline and her time to come there. So yes, she hasn't done any windows yet, but we need to pay her. She needs some money to pay for her trouble to come. And if you don't like that, think about it if you were a window washer. You'd want some money to pay for your time and your gas money to get there. And that's what these flat fees are all about. So is this relationship linear? We're now using some better linear relationship vocabulary here because it's asking about it right off the bat if this relationship linear. And this part that says $3 per window, that really indicates that it's going up by the same amount every single time. So if it's going up by $3 each window, then yes, this relationship's linear. Yes, it goes up by the same amount each time. And we talked about that at the start of the chapter. We've used that all the way through the chapter, and now it's come full circle. We want to talk about it again. It says create a table of values. So this is where the modeling comes in. We're going to try to take this situation and put it into some mathematics, and that's the modeling. We're taking a situation and we're going to make a model of it that we can use using math. So the table of values here would be n for number of windows. You might be addicted to X and Y at this point. You might like to use X and Y there. I don't always suggest that. I usually like to use letters that really represent what's going on in the situation. And for the dependent variable, the part we're going to figure out, I'm going to use C for cost. So how many windows can she do? Well, I guess technically she could do 0 windows. 1, 2, 3, 4, 5, 6. And for 0 windows, it's still going to cost that $5 flat fee, which seems a little stunning. But again, normally you're not going to have her come for 0 windows, so you're not really paying that $5 anyways. That $5 is for her time and her supplies and everything like that. And that's going up by 3 each time, so extra $3 for each window. So we go up to 8, 11, 14, 17, 20. I'm just adding 3s on there. And then it says create an equation to model the earnings here. Well, I'm going to really try to use y equals mx plus b here. I'm going to go over in the corner here and really talk about what we've been talking about all chapter, which is y equals mx plus b. And y equals mx plus b, to really review the whole chapter in one example, we really want that m is going to represent how much it's going up by. It's going to be the slope. It's going to be the rate. And here the rate is $3 per window. And then this b is the y-intercept. It's the start value. It's where the whole situation gets going, and that's 5. And I'm just using that in a little thought bubble here because that really fits with what we've been talking about this chapter. In this case, I was using c and n, so instead I'm going to go c equals 3 times n plus 5. And I hope me changing back and forth between the letters helped you, or the variables I used, helps you to really understand the relationship between y equals mx plus b and actual equations. I'm going to use c equals 3n plus 5. How are we going to get the charge for Christine? Well, she's going to go $3 times the number of windows, and then she's going to add her $5 flat fee. What are the independent and dependent variables? Well, that's not perfectly clear, to be honest, because it really depends on which way you're going to think about this. Most times you would think of it this way, is that you'd go, okay, well, how many windows do I want to get washed? Okay, maybe I look at my house and I got about 10 windows, so I plug that number in. And because you usually think of it that way, then the number of windows is the independent variable. You get to choose that. You get to decide how many windows you're going to wash. And from there, you figure out what it's going to cost. Okay, so it's likely that you'd think of the independent to be number of windows. And you think of the dependent to be the cost. Okay, there's another reason for that we sort of hinted at. In math situations, we usually put the independent in the first column, and we usually put the dependent in the other column. It's not a rule, but we really try and follow that so that we all do it the same way. Next, what is the slope of this relationship? The slope here is 3. It's how much the cost goes up for 1, and sometimes in general examples we just say how much does it go up for 1, but in this case we have the words available. In this case, how much the cost goes up for 1 window. What's the y-intercept of this situation? Well, we didn't use y, we used c. So c was our dependent variable, so I'm just going to change the wording in the question there. What is the c-intercept for the situation? And it's 5, and it's where the charges start. Is this relationship an example of direct or partial variation? If you can answer it already, that's great. I want you to think about whether it's direct or partial just by looking at that table of values in that equation. And if you think of direct and partial a slightly different way, you might want the graph first. So you might want to do H first and do this graph first. So here's my graph. I'm going to put that number of windows. 0, 1. Oh, I don't like where that showed up. Fix that up. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 windows. Now, 10 windows, let me just do a little thinking here. For 10 windows, 3 times each window is $30, plus the original 5 is 35. I'd really like my scale to go up to 35 if possible. Let's count the number of squares here. 2, 4, 6, 8, 10, 12, 14, 16, 8. I got 20 squares. I want to go up to 35. Or I could go by 2s. 2s will get there. I don't want to write on every line. It gets so messy. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 40. Okay, so that's going to work very well. I'm going to say cost here in dollars. I'm going to switch colors just so you can see my points on here. Let's see. What was it again? $5. Okay, so there's 5 right there. And then for 1 window, we're going up by 3 each time. So 1 window goes up to $8. 2 windows now $11. Then 3 windows, $14. 4 windows, $17. 5 windows, $20. 6 windows, $23. 7 windows, $26. 8 windows, $29. 9 windows, $32. And 10 windows, $35. So I graphed this relationship, and Christine's just going to put a title up here. When you start doing these things in science, they're really going to want a title at the top as well. Now, as I was drawing all those dots, if you were thinking, why don't you just draw a straight line with a ruler? And this is one of those situations. Technically, this is a discrete variable. We don't really burn you on this in grade 9 all that much, but I do want to mention I really shouldn't connect the dots here, because if I connect the dots, I'm implying that all the dots in between are allowed. And for a number of windows, that's not true. You can't really get 1.2 windows cleaned, so you really shouldn't be connecting these dots up, technically. If you do connect the dots up, no one's going to get too excited. The compromise we sort of came to is that if you want to draw the line on there and the dots shouldn't be connected, we usually do it with a dashed line. And we sort of go like this. And we say, well, we know it's linear. We know it goes straight like that. That's the pattern here that's going on here. But we shouldn't connect up the dots because we don't want to imply that you can have any continuous value, any decimal value in between there. So this sort of lets everybody know both at the same time. And now you're ready at the end to answer G. Maybe you were ready before. Direct variation means it goes directly through the origin. It goes through the point 0, 0. This does not. It starts part way up. So we call this partial variation. It's not just two numbers multiplied together. It's has a y-intercept that changes the cost there. If Christine just charged $3 per window and she didn't charge this initial fee of $5, then it would be a direct variation. Well, that's the kind of homework we're looking for. We like to take this full circle and do some word problems and really see all this stuff in action and use all these words and language we've got from the chapter. So really take a run at that homework. And that from there on, we're ready to do other types of word problems, and we'll get ready for those. And after that, sort of wraps up the